Organocatalysis. Introduction. Regular achural organocatalysts are based on nitrogen such as piperidine used in the noevanadial condensation, DMEC used in esterifications, and DAPCO used in the Bayliss-Hillman reaction. Thiazolium salts are employed in the Stetter reaction. These catalysts and reactions have a long history, but current interest in organocatalysis is focused on asymmetric catalysis with chiral catalysts, called asymmetric organocatalysis or enantioselective organocatalysis. A pioneering reaction developed in the 1970s is called the Hodges-Parrish-Edersauer-Weichert reaction. Between 1968 and 1997, there were only a few reports of the use of small organic molecules as catalysts for asymmetric reactions, the Hodges-Parrish reaction probably being the most famous, but these chemical studies were viewed more as unique chemical reactions than as integral parts of a larger, interconnected field. In this reaction, naturally occurring chiral proline is the chiral catalyst in an aldol reaction. The starting material is an achural triketone, and it requires just 3% of proline to obtain the reaction product, a ketol in 93% enantiomeric excess. This is the first example of an amino acid catalyzed asymmetric aldol reaction. The asymmetric synthesis of the Wieland-Miesser ketone 1985 is also based on proline, and another early application was one of the transformations in the total synthesis of erythromycin by Robert B. Woodward 1981. A mini-review digest article focuses on selected recent examples of total synthesis of natural and pharmaceutical products using organocatalytic reactions. Many chiral organocatalysts are an adaptation of chiral ligands which together with a metal center also catalyze asymmetric reactions, and both concepts overlap to some degree. A breakthrough in the field of organocatalysis came in 1997 when Yianxi reported the first general, highly enantioselective organocatalytic reaction with the catalytic asymmetric epoxidation of trans and trisubstituted olefins with chiral dioxiranes. Since that time, several different types of reactions have been developed. Organocatalyst classes. Organocatalysts for asymmetric synthesis can be grouped in several classes: biomolecules, proline, phenylalanine, secondary amines in general, the cinchona alkaloids, certain oligopeptides, synthetic catalysts derived from biomolecules, hydrogen bonding catalysts, including tadols, derivatives of banal such as nabin, and organocatalysts based on thioureas. Triazolium salts as next-generation Stetter reaction catalysts. Examples of asymmetric reactions involving organocatalysts are asymmetric Diels-Alder reactions, asymmetric Michael reactions, asymmetric Manish reactions, She epoxidation, organocatalytic transfer hydrogenation. Proline. Proline-catalysis has been reviewed. Imidazolidinone organocatalysis. Imidazolidinones are catalysts for many transformations, such as asymmetric Diels-Alder reactions and Michael additions. Chiral catalysts induce asymmetric reactions, often with high enantioselectivities. This catalyst works by forming an iminium ion with carbonyl groups of A, B unsaturated aldehydes, enols, and nones in a rapid chemical equilibrium. This iminium activation is similar to activation of carbonyl groups by a Lewis acid, and both catalysts lower the substrate's LUMO. The transient iminium intermediate is chiral, which is transferred to the reaction product via chiral induction. The catalysts have been used in Diels-Alder reactions, Michael additions, Friedel-Crafts alkylations, transfer hydrogenations, and epoxidations. One example is the asymmetric synthesis of the drug warfarin in equilibrium with the hemictyl in a Michael addition of 4-hydroxycoumarin and benzylide acetone. A recent exploit is the vinyl alkylation of crotonaldehyde with an organotrifluoroborate salt. For other examples of its use, see organocatalytic transfer hydrogenation and asymmetric Diels-Alder reactions. Thiourea organocatalysis. A large group of organocatalysts incorporate the urea or the thiourea moiety. These catalytically effective thiourea derivatives, termed Thiourea organocatalysts, provide explicit double hydrogen bonding interactions to coordinate and activate H-bond accepting substrates.